In the introduction to this section, we saw that trig functions are defined in terms of a ratio of the sides of a right triangle. Since angles determine the sides of a right triangle, the actual length of your triangles do not matter. Let's look at an example of this. Suppose we're given two right triangles. This first right triangle has sides 4, 3, and 5, and our second right triangle has sides 400, 300, and 500. Along with each of these angles being theta. Then, if we evaluate the trig function sine at our angle theta, for our first triangle we'll see that this is going to be equal to 3 divided by 5. And if we evaluate sine at our second angle theta of our second triangle, this is going to be equal to 300 divided by 500. Again, the radius of our circle is not what's important here. The important thing is that these triangles live inside our circle, a circle, and the angle theta is what is going to determine what the value of our trig function is. Again, we'll use the radius of length 1 for any unit circle, for any circle that we'll be working with. This is just for convenience and also convention. Let's rewrite the definition of our trig functions and then look at an example. Again, assume we have a circle. This time we're looking at a unit circle, which means the radius is given by r. Then the definition of our trig functions again is the following. Since we're assuming that we're now working with the unit circle, r is equal to 1, and our trig functions are going to simplify to be the following. This is equal to y, this is equal to x, this is still equal to y divided by x, cosecant theta is now 1 divided by y, secant theta is now 1 divided by x, and cotan is still x divided by y. Generally, anytime we'll be working with trig functions in this section, we'll be using the definition that can be found on this page here. Now, let's look at an example. Example number 1. We want to sketch a triangle that has an acute angle theta, and then find the other 5 trig ratios of theta. Here, we're given that the cotan of theta is equal to 1. So to solve this problem, let's go ahead and write out the definition of cotan. The cotangent of any angle theta is going to be equal to the adjacent divided by the opposite. Or if we write this in terms of xy's, this is going to be x divided by y. Let's draw a picture to keep everything in order. Here we have our unit circle. Here we have our point. And we're given that this cotan theta is going to be equal to 1 divided by 1. So we'll move over 1 unit in the x direction, and then 1 unit in the y direction. Then we have a line connecting to the point on our circle to the origin, given by r. We can go ahead and find r, since we know that this is a right triangle, by using the Pythagorean theorem, which means a squared plus b squared is equal to c squared. Or in this case, x squared plus y squared is equal to r squared. This is going to give us 1 squared plus 1 squared is equal to r squared, which means r is going to be equal to the square root of 2. Since the radius of a circle is never non-negative, we know this is going to be the positive square root. Let me redraw the triangle that we're given, or that we found all the sides for, and then we'll write out the other 5 trig ratios. Again, for sine theta, this is opposite divided by hypotenuse, so 1 divided by the square root of 2. This is equivalent to the square root of 2 divided by 2. Cosine theta is adjacent divided by hypotenuse, which is 1 divided by the square root of 2, again equal to the square root of 2 divided by 2. Tan theta is equal to opposite divided by adjacent, 1 divided by 1. Cosecant theta is hypotenuse divided by opposite, which is equal to square root of 2 divided by 1. And the last one, secant theta, is going to be equal to hypotenuse divided by adjacent, which is again square root of 2 divided by 1. These are the trig ratios that we're looking for associated to the angle theta.